The problem is from GATE 2016 mathematics paper, question number 16. The problem given is let Zn be a sequence of distinct points in D of 0, 1. That is given as Z in C such that mod Z is less than 1 with limit n tending to infinity Zn equal to 0. Consider the following statements P and Q, whereas the statements P is given as there exists a unique unlighty function f on d of 0, 1 such that f of zn equal to sin zn for all n. And the statement Q is there exists an analytic function f on d of 0, 1 such that f of zn equal to 0 if n is even and f of zn equal to 1 if n is odd. The NPTEL reference to solve this problem is Module 1, Lecture 2 of Advanced Complex Analysis Part 1. The title of this lecture is The Argument Principle, Roche's Theorem and the Fundamental Theorem by Dr. T.E. Venkat Balaji. He is from Department of Mathematics, IIT Madras. Even you can watch this reference video using this YouTube link. So now coming to the solution. This problem is nothing but a straightforward application of the identity theorem. Whereas the identity theorem tells us that, or okay, let me skip the theorem statement. So it is given that given Zn is a sequence in D of 0, 1 and limit n tending to infinity Zn equal to 0. So the important condition here is that the condition limit n tending to infinity Zn equal to 0. Based on this theorem, the two statements are dependent. That is, since let me write that since we can see limit n tending to infinity Zn equal to 0 and Zn is in sequence of distinct points is a, okay, let me write that sequence of distinct points in this disk. So Zn has a limit point 0 in D of 0, 1. So now coming to the statements P. So it is asked to check whether that there exists a unique analytic function f on D of 0, 1 such that f of Zn equal to sin Zn for all n. Since so we have to check whether there exists f of Zn equal to sin Zn for all n. By identity theorem, if f equal to g on a set on S having a limit point in D, then we have f equal to g on the whole domain D. By using this theorem, we have taking S as the sequence Zn n in when we take the set S as the given sequence Zn, then by the given condition it is already given that since Zn has the limit point 0, that is since n tending to infinity Zn equal to 0, that means 0 is nothing but a limit point, and obviously 0 is contained in this disk D of 0, 1. So we can say 0 is a limit point of this set S, which is contained in D. So 0 is the limit point of the set S in D. So by identity theorem, since Zn converging to 0 and f of Zn equal to sin Zn for all n, so we have f of z is nothing but sin z, where for all where z for all z in the disk 0 d of 0 comma 1. Since it is given f of zn is sin zn on the set s, but since s has a limit point 0, that is nothing but 0, sorry, s is nothing but, since s is nothing but the set of the points in this sequence Zn, and which has a limit point 0 in D. So we can say the function f of Zn becomes analytically equal to sin Z on the whole disk D, and whereas D is nothing but our given disk D of 0 comma 1. And so we have f of Z equal to sin Z for all Z in D, and hence, and we can see easily that f of Z equal to sin Z is the unique function, and there does not exist any other functions, and hence P is true. That is, given statement is true. But whereas coming to the statement Q, it is given that there exists unlinear function f on D of 0 comma 1, such that f of Zn equal to 0 if n is even, and f of Zn equal to 1 if n is odd. So firstly, let me assume the statement is true. Suppose the statement Q is true. That is, there exists an unlinear function f such that f of Zn equal to 0 if n is even, comma, f of Zn equal to 1 if n is odd. So now by this statement, I am considering the sequence Z2n only. Since it is given Zn is a sequence, so I can consider the subsequence Z2n, which is again a sequence, which is a subsequence, since Zn converging to 0. So we have Z2n is also converging to 0. So Z2n has a limit point in D, and since f of Zn equal to 0 if n is even, so by identity theorem we can say f of z equal to 0 for all z in D of 0 comma 1. But so when we consider the statement is true, when we assume the statement is true by the given condition that f of Zn equal to 0 if whenever n is even, we then we are getting f of z should be analytically equal to 0. But it is given that one more condition, f of zn equal to 1 for if n is odd. But in this case we have that implies f of z1 is also 0, f of z3 is also 0, and so on. F of 2n, sorry, z2n plus 1 equal to 0 for all n in n. But which is a contradiction to the given statement that f of zn equal to 1 if n is odd. But by the assuming, when we assume the given statement is true, we are getting f of z1 equal to 0, but it is given that f of z1 should be 1. So which is a contradiction. So there does not exist any such function. Hence the statement q is false. So we have only the statement p is true and q is false.